We're now going to talk about the fundamental equations of motion. They come from Newton's second law, which you're probably familiar with. We usually say F equals ma, right? So the force and the acceleration of this object are related. So we're going to write these equations in terms of the body fixed forces and accelerations. So the way we would do that is we're going to have surface forces, F sub s. So those are like the aerodynamic forces from on the surface of the object, plus body forces, which would be our weight vector. And that's equal to mass times acceleration. So in general, that's actually the change in time of mass times velocity. Okay, so that's ma. And then we actually end up with one other term over here, which we're called, it's kind of a fictitious force. It's called sometimes called Coriolis forces. And this is a force that appears on our object because it's accelerating relative to a different inertial coordinate system, okay? And so that is equal to omega. That's the rotation rate and that's a vector. It's about all three axes crossed with mass times velocity. Okay, so this is, these are called Coriolis forces, all right? Again, this is a fictitious force. It's just there because we're accelerating relative to a different coordinate system. Okay, so this is our F equals ma fundamental equation, and we're going to interrogate it a bit here and kind of rearrange it in a more useful form. I want to point out, though, that there is a similar equation for the moments. So F equals ma we usually think of in terms of translational forces and accelerations, but there's also a rotational equation that equates the rotational moments to the rotational accelerations. And so that is the surface moments is equal to the change in time. And this one depends on the inertia of the aircraft about the center of gravity. So that's the inertia tensor there times omega. That's the rotation rate plus omega cross the inertia tensor times omega again. Okay, so this is an identical equation, but that equates the moment on the aircraft to the rotational acceleration of the aircraft. Just like the first equation is translational forces and moments, or excuse me, forces and acceleration. So just real quick, we'll also say or define our inertia tensor here, I. That's the inertia tensor about the aircraft center of gravity in body fixed coordinate systems. Okay, so IXXB, IYYB, and IZZB on the diagonal there. And then we've got minus IXYB minus IXZB. And then down here we have minus IYXB and minus IYZB. And then we've got minus IZXB and minus IZYB. Okay, so this tensor is symmetric, meaning that these terms are equal right there, and actually these two terms right there are also equal. Okay, so it actually only has 6 components that define the inertia tensor. The 9 components of the inertia tensor, it actually only has 6 values, okay, because it's symmetric. Anyway, okay, so let's just define a couple things here. So our velocity and omega. So velocity is our translational velocity, and omega is our rotational velocity relative to the body fixed coordinate system, okay? And so for V, capital V, we're going to write that as u, v, w. Okay, that's our components of velocity, u, v, and w. And omega is our rotational velocity. And we're going to write that as P, Q, and R. Okay, so alphabetic triads, P, Q, and R is simply the rotation rate about each of the axes. So P is about the roll axis or the x-axis, Q is about the y-axis or the pitch axis, and R is about the z-axis or the yaw axis. Okay, just like U, V, and W are the velocity components along each of those axes, P, Q, and R are the rotation rates about those axes. Okay, so like I said, we're going to dig into this equation here and kind of mess with it just a little bit. The first thing I'm going to do is actually move this term over to the left-hand side and move these two terms to the right-hand side. So I'll just rewrite that here. D times mv is equal to, actually, I'm sorry, we're gonna leave those on the other side. Fs plus w. We're really moving this term over to get this guy singled out. So minus omega cross mv. Okay, so I just rearranged that equation. Now let's look at the left-hand side here. This is the derivative in time of mass times velocity. We're going to use a chain rule on this and say that, by the way, that little m stands for mass. And I know that's a little bit confusing because we've used little m for pitching moment. In this lecture here, little m stands for mass, and we're going to, by the end of this lecture, we're going to swap it out for something else so that we don't have to see it anymore, so we don't get confused with the pitching moment. But for this, it's easier just to write little m for mass. So if we do chain rule on this, then we'd have mass times d, or the partial with respect to t of v plus v times the change in mass with time. Okay, so that's just the chain rule there. And now at this point, we need to understand what this change in mass with time represents. So most aircraft are burning off fuel, right? So now that obviously wouldn't apply to a battery-powered or electric aircraft, but most aircraft in operation today are gas-powered, and so they're burning off fuel as a function of time, and so their mass is actually changing as a function of time. Now, not only are they changing in weight, but many of those aircraft are ejecting that mass at some significant velocity that creates a thrust, okay? And so that mass that's exiting can actually have a different velocity than the velocity of the aircraft. And so we need to add in another term here. This is the change in mass, or m dot e, the exit mass, times v e, the exit velocity. Now, the change in mass with respect to t plus m dot e, which is that exit mass, that has to be equal to 0. Okay, so now some aircraft are just using the mass to as a fuel, so they're burning it off like a propeller, an aircraft that's using a propeller, but it still has some exhaust. So that mass is still exiting the aircraft. That exhaust is exiting, but it doesn't have a lot of a big change between the exit velocity and the velocity of the aircraft. But other aircraft can actually be using that mass as more of a thrust term. So like rockets, for example, and other aircraft can actually change their mass very rapidly. So, for example, bombers who are dropping a significant weight of their aircraft, crop dusters, firefighting aircraft that go and scoop up water and dump water, they can be changing their mass very rapidly. Okay, m dot e, although we think of that as being positive as it mass exiting the aircraft, it can actually be negative if an aircraft is gaining mass during flight, which is the case for like a in-air refueling situation. So anyway, these are all things that we need to be able to account for. And what we're going to do is we're actually just going to take these two terms and add them together. And we're going to, this is basically a thrust term that we're going to call m dot. This is the change in mass with respect to time, which they're equal and opposite. So it's going to be m dot times VE, the x velocity, minus the velocity of the aircraft, okay? So we're going to combine those two terms together, and we're actually going to add this now to our total, to our surface forces here to get a total force on the aircraft. Okay, so the total force, this is going to be aerodynamic plus thrust, is going to be our surface forces that come from a surface pressure on the aircraft, for example, minus m dot VE minus V. Okay, so this is these are our surface forces, these are our thrusts, and we're going to just include all of that in a total total force, what we can call the aerodynamic force on this aircraft that includes the thrust. Okay, so now so the left-hand side of this equation has simplified quite a bit. So we're going to get m times d dt of v is equal to, and now for this term right here, so I've used this term here for the left-hand side because we're moving this stuff over into this term here. So that's going to be equal to the total aerodynamic force vector plus our weight vector minus omega cross mv. Okay, so and again that total force vector now includes thrust. So we just want to be careful not to double count thrust, okay, or this mass that's entering or exiting the aircraft. But as long as it's all wrapped up inside of that capital F term here, our force vector, then we should be good. So now let's take this term here and pick it apart just a little bit. So we're going to write omega cross mv, and we can do the cross product there, where instead of capital V, we're going to use our UVW, and instead of omega, we're going to use PQR. So we can just do the cross product of that, and what we'll get is m times QW minus RV, and then RU minus PW, and PV minus QU. Okay, so that's the cross product there. And now we can take this term, substitute it in for that, and write a final equation here in a slightly different form. So now this velocity vector I'm now going to write in terms of UVW. I'm going to break out the components of force and weight, and then we're going to use this term here for this final term here. And what we get is, and one last thing for mass here, we're going to use W over G, okay? So I'll just make a note there, mass equals W over G, okay? So we're going to swap that out as well. Okay, so the final version of this equation, what we get is W over G times U dot V dot W dot. So that's a change in velocity with respect to time, right? So this is UV and W, but with the change with respect to time, so we're going to put a dot above those. And that is equal to, now I'm going to break out my force vector. So it's the force in the x direction, the force in the y direction, and the force in the z direction. And again, that includes the thrust force, plus the weight in the x direction, the weight in the y direction, and the weight in the z direction. And then plus, and then instead of this m right here, we're going to use W over G again for mass. So we're going to have W over G times that top component, which is RV minus QW, and I've changed the order here because we had a minus sign right here that I'm going to bring inside of here. So that becomes positive, the RV right there, and the minus QW right there. And then the same with the next one, plus W over G times PW minus RU, and W over G times QU minus PV. Okay, so this is simply Newton's second law. This is our F equals ma equation. We've just rewritten it. We've rearranged it. We've included thrust inside of this force vector, and that's going to include our change in mass with respect to time that's exiting. Now, what this means is that see this m over here. We've already included the effects of changing that mass with respect to time, okay, this dm dt term here. And so what that means is that this mass here can actually be a function of time. So these equations here, although it looks like W is a static value, that W can actually be changing with time because we are including the effects of that, the thrust effects that come from that, or the change in mass with respect to time in this force vector here, okay? So W can now be a function of time, and so this is our final form that we'll be then using for Newton's second law in the translational sense. Now, again, we have this other equation here that is Newton's second law for rotation. For the rotation of the aircraft, and I'm not going to work through that. You could work through this the same way. But one thing that I want to point out is that when we work through that, or the way we're going to use it first, is we're going to actually assume that that the aircraft is symmetric about the XZ plane. Okay, so most aircraft are very nearly symmetric about the XZ plane. And so what happens for that is that these terms right here go to 0. Okay, so our inertia tensor, we're going to assume those 4 components go to 0. And what that does is it allows the longitudinal and lateral components to be divided up just a little bit. And so we're going to be able to study the motion of the aircraft in longitudinal form and then in lateral form, somewhat independent of each other. And then at the end, we're going to come back and put those terms back in and get a general solution for an aircraft that is not perfectly symmetric about the XZ axis, so, okay, or the XZ plane. Okay, so if we were to walk through this development, and again, I'm not going to go through it in detail, but it's similar to what we just did here with the with F equals ma. Then what we would get for this second equation is Ixxb, Iyyb, Izzb, minus Ixzb, and minus Izxb. And then we have zeros right here because we're assuming that that's symmetric. That's multiplied by P dot, Q dot, R dot. So this is our change in our rotation rates of the aircraft, is equal to mxb, myb, mzb. And again, these moments now are not just surface moments like they were before. So remember we had this as the surface moments here, but we're now including the effects of thrust on that and the changes in our moment of inertia tensor as a function of time. And so this now includes thrust. So it's surface plus thrust. And then what we get here is plus Iyyb minus Izzb times QR. Here we get plus Izzb minus Ixxb times PR. And finally Ixxb minus Iyyb times PQ. Okay, and then we have one last term here for each of these. We're going to have an IXZ times PQ, an IXZ times R squared minus P squared, and an IXZB times QR. Okay, so this is F equals ma, but for the rotation rates of the aircraft. Again, this inertia tensor can be a function of time just fine, because we've included the effects of thrust and the effects of changing that inertia tensor as a function of time due to fuel or mass entering or exiting this aircraft inside of these terms here. Okay, so these six equations now, these are six equations that basically tell us our accelerations u dot v dot w dot and p dot q dot and r dot as a function of the current state of the aircraft, the current forces, aerodynamic including thrust, the current weight vector, and the current rotation rates p, q, and r, and UVW here, our velocity. And same thing here. If we have a current inertia tensor that can be a function of time, we can now compute the change in our rotation rates, P, Q, and R, as a function of the current aerodynamic moments, including thrust, the current inertia tensor, and the rotation rates, P, Q, and R. Okay, so these are now our fundamental equations that we're going to be using and look at different ways of solving these equations.